Okay, welcome back, everyone. I'm just starting by sharing this picture of the real and imaginary parts of a holomorphic function, i.e. some of the level sets of two harmonic functions that are harmonic conjugates of each other. This is our friend cosine of z, and among the features you can see in this diagram, one of the prominent ones is this cross in the middle. That's occurring not because cosine z vanishes there, but because its derivative, sine z, vanishes there. And at a place where a harmonic function has a zero derivative, it has to have a sort of a saddle shape, and consequently the level sets come together. In this case, at a simple zero, the level sets of one of the, say, the real part of cosine, they form a cross in one direction, and the level sets of the imaginary part form a cross that's rotated by 45 degrees. So these singularities of the level sets are actually the only kind of singularities you see when you look at the gradients of harmonic functions. One thing that can happen is the zero can be of higher order. If it's a double zero, then you'll see 6 level sets coming together instead of 4 at each of these singularities. So I just wanted to share that as a new picture that's been added to the notes relevant to our harmonic discussion. Okay, so today I want to work in the direction of harmonic measure, which is a new kind of conformal invariant. It gives you a number attached to a domain and a set on the boundary. But to get there, we're going to have to solve the Dirichlet problem. But we're pretty close to solving that because we saw how to solve it on the disk last time. And one of the important points about the Dirichlet problem is that if you can solve it on one domain, then you can solve it on any domain that's conformally equivalent to that domain, as long as things work out okay with transporting boundary values back and forth. That's a sign of the conformal invariance of harmonic functions. And before I address that, let me discuss this Dirichlet energy again, which is in some sense more primitive than the Laplacian. So the Dirichlet energy of a function on a domain in the complex plane, let's say a complex valued function, but not necessarily analytic, is given by integrating over the domain the differential of the function wedge the star of the differential. And if f is complex, you need to put a bar here as well, and then this will be greater than or equal to 0. So this is called the Dirichlet energy. And the first thing I want to point out about it is that it's a conformal invariant. So if we had a map, an isomorphism from another domain, omega prime, to our first domain, H, say we had a holomorphic homeomorphism, then we would get a new analytic function or a new smooth function on omega prime by pulling back. And then we can compute the Dirichlet energy of this by integrating over omega prime. And we get the same answer as we get by integrating the original function of omega. And the reason for that is very simple. It's because the exterior differential behaves well with respect to smooth mappings, and the star behaves well with respect to conformal mapping. So this is an intrinsic invariant of the function f. Now notice you might have said, oh, what, and L2, that also is an intrinsic invariant, right? But no, of course not. This integral, the L2 norm of f squared, is not invariant under change of coordinates. If you pull back f under a map that is given by z goes to 2z, the volume form will change. There is no, you could take the integral, say, with respect to the hyperbolic metric, but this Euclidean volume form is not invariant under analytic changes of coordinates. And so the L2 norm is also not invariant. But somehow this quantity is invariant, and this quantity is also an L2 norm. This is the same as the integral of the gradient of f squared dz squared. And yet it remarkably is invariant. So how could it possibly be invariant when this quantity is not? The reason is that the gradient is also not a natural quantity. To form the gradient of a function, you need a metric. So this area is not quite natural. The gradient is not quite natural, but they're failed to be natural in sort of different ways. If you like, there's a dz on the bottom here, and there's a dz on the top here, and since this is squared, they cancel out. And the result becomes this conformally invariant expression here. Now, to make the Dirichlet energy less mysterious, let me also tell you a very simple interpretation for what it means. So I'll sum this up as a theorem. The Dirichlet energy is conformally invariant and if f equals alpha plus I beta is an analytic function, then we have two harmonic functions. Then the Dirichlet energy of alpha is the same as the Dirichlet energy of beta, and the two put together are 1/2 the Dirichlet energy of f. And the energy of f turns out to have a very simple expression. It's the area of f of omega counted with multiplicity. So for example, if f is a Riemann mapping, then this integral gives you the same thing as the this integral gives you the same thing as the area of the image of the Riemann mapping. That's the meaning of the Dirichlet energy. If f happened to be 2-to-1, you would get twice the area. If some parts are covered more than once and some parts not, you would get the area weighted by the multiplicity of the fibers of f. So that's what we're trying to minimize when we solve the Dirichlet problem, is in some sense, if we had available the harmonic conjugate, sorry, this should have been beta. If we had available the harmonic conjugate, we could form the corresponding analytic map and try to minimize the area of the image. So in this sense, a harmonic function is somehow related to minimal surfaces. Okay, so why is this true? It's true for the very simple reason that let's just look at what happens if f of z were z. So if f of z is z, then we would get dz wedge star dz bar as our integrand. And this is just dx plus I dy wedge. And now we have to star everything, so we get dy. But now we star everything and we put it in a bar. So we get dy again plus I dx. So I starred, and that changed the dy to a dx. And let's see, did I do this right? With a minus sign, but then I required an additional minus sign because I barred the I. Okay, so what does this work out to? Well, we're going to have some complex terms, but they're all zero, I dy dy and I dx dx. The only interesting thing is dx dy, and then we get plus I dy dx times I dy dx. the two i's give a minus sign, but the fact that these terms are in the wrong order gives another dx dy. So we get 2 dx which dy, which is just twice the area form. And so what we're integrating here is this area form pulled back under the mapping F. And that's almost the definition of the area of the image with multiplicity. Okay, so that's a few words about the Dirichlet energy. It can be used to construct something called the Gaussian free field, which we will revisit when we start discussing probability theory. Okay, so now let's go on to the Dirichlet problem. And let me sum up some of what we're going to show. So first, we've seen, so the problem is, let me say what the problem is. So we have a domain omega contained in C, and the problem is to construct a map P from the continuous functions on the boundary of omega to what I'll call the harmonic functions on the closure of omega. That sends a mapping phi to a mapping little phi, where phi restricted to omega itself is harmonic, and phi restricted to the boundary of omega is equal to our boundary data. That's our problem, is to construct this operator for all continuous functions on the boundary. And so we've solved this for the unit disk being omega. And we will quickly see that using the Riemann mapping theorem, we can solve when omega is a Jordan domain. And then one of our goals will be to solve when omega is a reasonably tame region, but not a Jordan domain. For brevity, I'll call this a finitely connected region, a finitely connected domain, which means that the boundary of omega is the union of Jordan curves, finitely many. Okay, so here's a case. This might be called a triply connected region because it has 3 boundary components. And by the way, then by some limiting argument, we'll get something that's sort of like a solution in fairly general cases. There's a lot of technicalities in doing the general case, and most of what we want to do, we can do by skirting that more general case. So that this will really be the main things we need to discuss. But there's one nuance which I want to add about going beyond the strict definition of this problem, which is that we'll sometimes want to deal with piecewise continuous data. Bounded phi. And so what this means, for example, if phi is a function on S1, which is the boundary of the disk, is that we'll allow functions which go along like this, and they're continuous, and then they make a jump. And then they go along continuously, and then they make a jump, and so on. So we'll also want to allow functions like this. So if you like, the domain is tiled into a union of arcs. The arcs meet only at their endpoints. And if we have a continuous function on each arc, but we don't require that they agree at the endpoints. That's the idea of piecewise continuous data. And so a nice example is to take the unit disk and take the boundary data, which is equal to 1 on the upper edge of the disk, and is equal to 0 on the lower edge of the disk. So in fact, this piecewise continuous function has an extension to the interior of the disk that's harmonic. Now, what do we mean by it being an extension? Well, we require that this hold, in other words, the limiting values of phi on the interior are equal to the boundary values, except possibly at these endpoints. So when we have piecewise continuous data, there's two requirements. We require that phi is bounded and that phi of z to the n tends to capital phi of a if z to the n goes to a and phi is continuous at a. So we want a function that is equal to 1 in the upper disk and 0 on the lower disk and is otherwise harmonic. Now, what is the meaning of this function? Let me ask, for example, what is the value of this function at the center of the disk? There's only one possible choice for its value at the center.
Half?
Yeah, it has to be a half by symmetry, or if you like, by the mean value theorem. So what this function is telling you is, if we think about it geometrically, it's the visual size of the northern hemisphere as seen from this point in the unit disk using hyperbolic light rays. So if you choose a geodesic at random from the origin, the chance that it lands in the northern hemisphere is exactly a half. And as we saw, that's one definition of the Poisson kernel. So when we have even discontinuous boundary data, we can solve the Dirichlet problem using the Poisson kernel, and the answer has the required coherence with the boundary values. So the harmonic extension has the property that it gets bigger as you go towards the northern hemisphere. It gets closer and closer to 1 because a random geodesic has a higher and higher probability of landing there. And in fact, you could figure out exactly what this function is by drawing the hyperbolic geodesics from z to plus or minus 1 and then measuring this angle between them. And that angle, or rather its complement, divided by 2 pi would give you the value of the harmonic extension. So we could do that. We could also write a formula for this, but let me simplify things a little to finish this example. Of course, the upper half plane is the unit disk is isomorphic to the upper half plane, and we can choose the isomorphism so that the southern hemisphere goes to the minus real axis, or actually, let's say it goes to the positive real axis. Here's the southern hemisphere, here's the northern hemisphere. We choose an isomorphism like that, and solving the problem here is the same as solving it there. And here, there's an obvious solution. So we want a function that's 0 here and 1 here. And by symmetry, the level sets of this function should look like this. They're just straight lines. So what's an example of a nice function that's constant on radial lines?
Argument?
The argument, right. So we haven't used it that much, but the argument of z is, after all, the imaginary part of the logarithm of z. And therefore, it's a harmonic function. So this function that goes from 0 to 1 is nothing more than the argument of z divided by pi. And that's the solution to the Dirichlet problem with boundary values 0 and 1 on these two parts of the boundary of the upper half plane. And of course, the solution here will have almost the same form, except it will be the argument of a Mobius transformation. That Mobius transformation being the one that provides this isomorphism. So this is an example where we solve the Dirichlet problem with discontinuous boundary data. So let me make a remark about that, just to give you confidence that this can be done. In fact, one can do much better than just discontinuous boundary data. There's a theorem of the following type. The Poisson kernel determines an isomorphism from the L infinity functions on the circle to the bounded harmonic functions on the unit disk. So here we take a function which is only measurable, but at least it's bounded almost everywhere. At the end of the day, we get a harmonic function on the unit disk, and this harmonic function, of course, has the value property that phi is at r theta is given by the convolution of the Poisson kernel at radius r with the boundary data phi, just as it was for continuous functions. And what's the coherence between the right and left-hand side? It has the boundary values here, even the values of this function might not exist on a dense set, but they do exist almost everywhere. And the coherence is that the radial limit of the function phi of rz is equal to capital Phi of z for almost every z in the circle. So the Poisson kernel is it's beautiful and smooth and so on that you can pair it with almost anything on the circle. You could pair it with L infinity functions, you can pair it with L1 functions, you can pair it with distributions. And I'm just giving you a sample case. If you have measurable boundary data, you get a harmonic function, and it turns out that the converse is true. If we take a bounded harmonic function on the disk, then this limit exists almost everywhere. And that defines a function capital Phi here, whose extension is the original little phi. So indeed, it's often true that suitable classes of harmonic functions, such as bounded ones, are uniquely determined by their boundary values, but the boundary values might not quite be defined everywhere. Anyway, this goes far beyond the piecewise continuous case, which is all we're going to need in our applications. Okay, so let's go down our list. How about solving the Dirichlet problem for a Jordan domain? Well, this is really easy. This is what conformal mappings are for. And this is a big difference between dimensions 2 and 3. In dimension 2, you could figure out the Poisson kernel and solve the problem on the sphere, and then it would be a big technical problem to extend that to Jordan domains. In fact, it's not even clear what a Jordan domain should be. Maybe you want to require the boundary has some smoothness. It gets kind of complicated because there is no Riemann mapping theorem. But for us, going from 2 to 3 is immediate. So theorem, the Dirichlet problem has a solution on any Jordan domain. The proof is just this. Let f from delta bar to omega bar be the Riemann map and remember that for Jordan domains, the map extends to the circle continuously, and in fact, it gives a homeomorphism from the closure of the disk to the closure of the image. So extended to S1. Then, how do you extend a function on the boundary of omega? So we start with a function on this fairly tame region omega. All we do is we pull it back to get a function on the boundary of the disk using this extended Riemann mapping. So that's just phi composed with f. Then we extend it to the inside here. And then we transport that back here by forming the function phi composed with F numbers. So the Poisson operator for omega is just the following. You take phi composed with F to get a function on the circle, apply the Poisson operator for the disk, and then take the end result and compose with F numbers. Okay, and since harmonic functions are transported to harmonic functions under analytic maps, everything works out perfectly. So there's an example in the notes, which is very pretty. Namely, you can take the region 0, 0, 0. You can take a unit square, S, in the complex plane, and take the boundary values to be 1 on an arc, and 1 on one side and 0 on the other 3 sides. And in fact, as we saw, even piecewise continuous data has a solution for the Dirichlet problem. So the same thing is true here, since F sends piecewise continuous data to piecewise continuous data. So it doesn't matter that this is piecewise continuous. And what does the solution look like? Well, it has the level sets all go through the corner here. And they give you, as I said, something you can think of as the level sets of temperature in a refrigerator where these 3 edges are held at a temperature of 0 and this edge is held at a temperature of 1. And indeed, this solution can be written down using the not quite the Riemann, the inverse of the Riemann map as described here, namely the Weierstrass P function for the square lattice sends this unit square S that we started with to the upper half plane, as we've discussed before, and we can arrange that it sends this edge to say the interval from 0 to 1. And now we're faced with an interesting problem of solving the Dirichlet problem in the unit disk with this boundary data, but we just did that with almost identical boundary data. So there should be a solution whose level sets are circular arcs based at 0 and 1. And then the Riemann mapping will transport that back to a solution in the square, because this is supposed to be 0 here and 0 here. I'll mark the 0 set in red. This white. Oh, I marked the wrong set. Never mind. And this function, the extension in the upper half plane of the indicator function of an interval, is just as simple as this extension for the positive real axis. In fact, let me say in general, if you have the interval from A to B, and you want to find the function that's 1 here and 0 here, it's given by phi of z is 1 over pi times the argument of z minus b minus the argument of z minus a. So both of these arguments are harmonic functions, as we've seen. And on the boundary, if you're over here, the argument of z minus a and the argument of z minus b are the same, because an arrow from z to a or b points in the same direction. Similarly here, but in between the, and maybe I reverse things. Let's see, did I want to do A first? Yeah, I think I want to do A first. Okay, so in this region, if you're here, then the argument of z minus, oh no, I had it right. The argument of z minus a, let's see. Okay, the argument of z minus b is, what is z minus b? Okay, so if this is 0, then this argument is, then z minus b is negative because it's less than b, and so this argument is pi, whereas z minus a is positive, so this argument is 0. Pi minus 0, 1 over pi gives 1. Okay, so this solves p of the indicator function of the interval from a to b is equal to theta. Okay, so in that way you can solve the Dirichlet problem even with piecewise bounded data on an arbitrary simply connected region. So arbitrary Jordan domain. So the really interesting part is how can you go from Jordan domain to general regions, because we don't have a Riemann mapping theorem. But before we do that, I want to just make one little point for purposes of security, which is that when we solve for piecewise continuous boundary data, we want to make sure the solution is unique. And this is ensured by something called Lindelof's theorem. And usually we would say it's ensured by the maximum principle. But the maximum principle may not work when we allow a discontinuity on the boundary. So there's a theorem, let me say it this way. The Dirichlet problem has a unique bounded solution on a given domain with boundary data that is bounded and continuous outside finitely many points. A1 up to AN in the boundary of the domain. And this would be false if we didn't put in the word bounded here. And the reason is that if you remember the Poisson kernel, so this is a counterexample. Our good friend the Poisson kernel, which is on the unit disk, 1 minus c squared over the absolute value of 1 minus c squared. This tends to 0 at every point of the circle, except for the point 1. And so we have a function which tends to 0 with one exceptional point, and yet it's not identically 0. That shows the maximum principle does not hold for harmonic functions that don't have boundary values everywhere. But the thing is, this function is unbounded. It goes to infinity as z goes to 0 because of this, as z goes to 1 because of this term here. So this blows up radically at the point A. And if we were to require that P of z is bounded, the fact that its boundary values are 0 almost everywhere implies that they're 0 everywhere. So to get a unique solution to the Dirichlet problem, we need to require that the solution is bounded. And since we have bounded boundary data, of course, that's a very natural requirement. So this theorem is really a corollary of the corresponding maximum principle, which says a bounded harmonic function is controlled, its supernorm is bounded by its boundary values, provided we, even if we're allowed to omit finitely many points. Okay, so let me just say the idea of the proof. So I need a name for my given domain. I'll call it omega. So we're trying to solve a problem on our domain omega. Let's pretend that it's bounded. Say the diameter of omega is r. But there's a finite set of points where we don't control the boundary values. And let's say everywhere else, the boundary values are less than or equal to m. So the idea is, suppose phi of z extends capital Phi outside A1 up to AN. Then we let phi sub s of z, phi of z, and then what we do is we add on a small term here, s plus the sum from 1 to n of this function log z minus ai over the radius or the diameter of our set omega. So we have this function phi on the inside and we can't quite control it. We know it's bounded by m, except it might do something weird at these points. And what we do is we add on this function. Now, how does this function behave? As z goes to ai, the logarithm goes to minus infinity because z minus ai goes to 0. So this function goes to minus infinity at ai. It's everywhere negative because z minus ai is less than the diameter of omega. And of course, it's harmonic. So the maximum principle applies to this plus this. The negativity ensures this is less than phi of z. Now, what can we say about this function? Well, since this goes to minus infinity at the AIs, and elsewhere the function goes to something that's at most m, the maximum principle implies that this sum is bounded by m on the inside omega. And it's limiting. If we took a sequence of points tending to its maximum value, they can't converge to the AIs because this function tends to minus infinity there. And if they converge to a point on the rest of the boundary, then they're bounded by m. So this function is certainly less than or equal to m in all of omega. But if we let s go to 0, then this quantity tends to 0 uniformly on compact sets. And so this quantity converges to phi as s goes to 0, and therefore phi itself is bounded by m. Now, how did I know that things went to minus infinity? Actually, what I needed was that this whole sum tends to minus infinity at ai, and that's because phi was bounded, whereas this is going to minus infinity. So that's where we use boundedness. Okay, this is called Lindelof's theorem. And it's the basic uniqueness theorem one should just have available for security when dealing with boundary data that might not be continuous. Okay, so now comes, I think, one of the most beautiful arguments in potential theory. This is the proof that the Dirichlet problem has a solution on a multiply connected domain. Okay, so you might think, gosh, we're stuck. We know how to turn Jordan domains into disks, but we don't know how to turn a triply connected domain into a disk. What should we do? So I'm going to give you just for concreteness, I'll show you how this works for an annulus, but the same argument works for an arbitrary finitely connected domain, and it uses some topology. But so the proof will be by what's called Schwarz's alternating method. This is a really amazing idea, I think. So Schwarz is trying to solve, let's say we have a region which is, actually I shouldn't draw it so it's so tame. We have a region which is doubly connected. Okay, this is our domain omega. And we know how to work with Jordan domains. So what we do is we first create a Jordan domain. So we do that by introducing an arc A here that joins the inner and outer boundaries of omega. And then what's left over, we call U. Now U is not literally a Jordan domain because it comes around and touches itself, but it's a limit of Jordan domains. And so you could, for example, take the square root and open it up, and then you would actually get a Jordan domain where you can solve the Dirichlet problem by our existing theorems. The main point is that this region, once you've cut along A, is now simply connected. And the Dirichlet problem is in fact solvable on this domain U. So that's great. So what we could try to do is solve the Dirichlet problem on U for given boundary data phi. But there's a couple of problems. One is we don't even know what the boundary data should be on this arc A. And the second thing is, once we solve the problem, why should the answer be harmonic on A? So that's a first step, but it certainly doesn't get us all the way. But now here's Schwarz's great idea, is he says, let's also take another copy of this domain. I should really be drawing this on the same board, but to keep it from getting confusing, I'll draw a second copy. Let's also slit along a different arc B, disjoint from A, and create a second region phi that's also simply connected. And now we can solve with boundary data on the boundary of phi. And then that will only have the problem that it might not be harmonic on B. Now, and we'll put the same boundary data on the boundary of omega in both cases. So the only difference will be what are we going to choose for boundary data on A and what are we going to choose on B. And then Schwarz's idea is to go back and forth between these two domains and solve so that you get a sequence of functions which is half of the time harmonic on A and half of the time harmonic on B. And then if you take a limit, it'll be a uniform limit of functions that are at least some of the time harmonic on both A and B. And so on the limit, it will be harmonic on the domain omega. That's the idea of the alternating method. Okay, so let's do it. So we suppose phi is a continuous function on the boundary of omega. And we can assume that it's bounded by 0 and 1, just by multiplying and scaling. So now we will construct a sequence of functions u1 greater than or equal to v1 greater than or equal to u2 greater than or equal to ... on omega bar such that ui is harmonic on u and vi is harmonic on v. And the boundary data of ui restricted to the boundary of omega will be the same as vi restricted to the boundary of omega, which will be our original boundary data capital phi. Okay, now how do we determine these functions? Well, we've already said what u is on most of the boundary. So u1 will be equal to phi on this part of the boundary, on both the inner and outer boundaries of omega. But what should we set it equal to on A? We don't know what we want it to be. But we do know that phi is bounded by 1. So if we set u1 equal to 1 on A, u1 should be bigger than the ultimate solution that we're working for. Because if there were a harmonic extension, then it would have to be less than or equal to 1 on A by the maximum principle. So we let u1, so we have these two arcs, A and B. And what we do is we define U1 so that it's just identically equal to 1 on A. And now we solve the Dirichlet problem in U for those boundary values. Okay, and then we get something. And who knows what it is on B? Well, let's just call it U1. It is what it is on B. Okay, but now that we're started, it's pretty clear how to proceed. We now have to solve a boundary value problem on V. And what we do is we take the answer that we got from U1 on B, and we feed it in to the Dirichlet problem for V. So here we have V1, and we let V1 be U1 on B. And of course, it continues to be phi, this is V1. It continues to be phi on the boundary here. Okay, so we get our next solution, V1. And by fiat, V1 is equal to U1 on B. And then we solve the Dirichlet problem in V to get it everywhere in omega, and in particular to get it on A. Now, what can we say about what it is on A? Well, what we know is that all of its boundary values are less than 1. So here, it is what it is, but it is certainly less than or equal to what U1 was. So if we now look on the common boundary of A and B, we see that U1 is above V1 everywhere on omega with both slits A and B removed. So by the mean value theorem, we have U1 is the mean value principle, or the maximum principle, we have U1 is greater than V1. So indeed, we can imagine slitting our domain into U into 2 domains by cutting along B. And then the maximum principle applies to the restriction of U1 to those regions. Its boundary values are the same on omega, and on A and B, V1 is less than the boundary values of U1. So V1 is less than U1. Okay, good. Now what should we do? Well, we now go back and we fix what happened for the U1. That is, we now have this function V1 defined on all of the region, and we go and redefine U1 to be equal to V1 on A. So that's how we get U2, is we put down V1 on A, and then B just comes out to be whatever it is. It's some new value U2. Okay, but what we notice is that U1 on A started out being 1, now it's something less than 1. So we can conclude that U1 is greater than or equal to U2 everywhere. And so in particular, U1 on B, U2 on B is less than or equal to U1. And so that shows U2 is less than or equal to V1. And now you can imagine you just continue. You look at V2, you specify its values on B to be U2. On A, it comes out to be whatever it's going to be. But since its boundary values on B have gone down, V2 must be less than V1. So continuing in this way, we get a decreasing sequence of functions which are alternately harmonic on U or on V. And now we use 2 beautiful facts. One is a decreasing sequence of functions that's bounded below, because all of these are positive because of the fact that phi was bounded below by 1. A decreasing sequence has a limit. So now we at least have something we can get our hands on. So we define phi of z to be the limit of ui of z in omega. And that's the same as the limit of vi of z. But if we look at the first limit, what we have is a sequence of functions that are harmonic on u, and they're bounded below and above. And so their derivatives are controlled, so they converge uniformly on compact sets. And the uniform limit of harmonic functions is harmonic. So this function is harmonic on u. this function, by the same reasoning, is harmonic on V. So phi is harmonic on the union of U and V, which is equal to omega. And so we're almost done. The last thing we have to prove is that, in fact, the boundary values of phi ended up being what they should be. That's a slightly technical step, but let me just say how it's done. You pick a point P where you want to check that the boundary values of phi agree with capital Phi of P, and you just draw a little arc around it like this. And now we're back to a simply connected domain. And so we have a simply connected domain, and we have data which is phi here, and which is, say, ui here. And the ui are tending to some function, this function phi. And we just have to show that as ui goes to phi, and these boundary values are kept fixed, that in the limit we get a solution which still has the same boundary values. So that's a simple calculation using the fact that ui is bounded and the behavior of the Poisson kernel, which ensures that when a point is very close to the boundary of omega, the boundary values of capital Phi make much more impact on the value of its harmonic extension than do the values on this distant arc over here. Okay, so that's one method to solve the Dirichlet problem on a finitely connected region. Okay, so this has been a kind of long story. Let me just pause for a second and see if there are any questions.
Is this going to give a unique solution?
Yes, that was the point of Lindelof's theorem. So there's two things. One is, I actually said we were going to construct this operator here. So I started with continuous boundary data on the boundary of omega here. So the usual maximum principle shows there's a unique solution. But if I wanted to allow piecewise continuous data on these Jordan arcs, then the Lindelof's maximum principle would show that that also has a unique solution. So one of the great ideas in this theory is that if you believe the solution exists, you can find it. And usually, because of the fact that it's unique, any scheme you find to construct it will work. Other questions?
So, like, if you instead tried to solve it just with the boundary data of the circle of the outside, not the inside,
Yeah.
then you get a different unique solution. So, can you say that if the data on the inner thing is different, then you can guarantee that if you tried to extend it, that it would have a point of divergence?
Okay, so I think what you're saying is let's change our scheme completely and say what we do is we start with phi on the outer boundary, and this region is a Jordan domain. So now we just extend it to a continuous function across the inner boundary. Is that what you're saying?
Yeah.
Yeah. So of course, when we do that, we get a harmonic function, but it might not agree with the boundary data that we've been given on the inner boundary.
So it's like if they differ, then you can assert that it will not like extend harmonically inside.
Oh yeah, of course, right. So if for some reason these boundary values happen to be the boundary values of a function that's harmonic of a whole region, then you would have to reproduce that function. Yeah, right. So usually what happens, a typical thing that we want to do is say have a function that's 1 on this boundary and 0 on this boundary. And it does have a harmonic extension to the inside, but there it's identically 0. And outside here it's not identically 0. So you have two harmonic functions fitting together continuously along a curve, but they're not harmonic on that curve. Another thing that's suggested, which I'll leave it to you to think about, but it's kind of interesting, is why not do the following? You just solve for the boundary data phi here, and then that gives you some boundary data on the inside, which is wrong. And then you solve for the difference between that boundary data and anyway, you could try to alternate between the inside and the outside, but I don't think it works. And the reason is that you're not allowed to change the boundary values on the inside and the outside. The reason this works is we are allowed to choose whatever boundary values we like on A and B, because we don't even know what they're going to end up being at the end of the day. Okay, so it gives us a fair amount of confidence in the fact that the Dirichlet problem can be solved. And now I want to turn to make a complete conceptual shift in how we think about this problem. And that shift will introduce the notion of harmonic measure. Okay, so suppose we have a solution to the Dirichlet problem. So suppose we have this. Okay, so we have our domain omega, and we have continuous functions on the boundary of omega, and we have a point z inside of omega. We can then take our operator here, p, that sends continuous functions on the boundary to harmonic functions on the interior, and just compose with evaluation at the point z to get, let's say, a real number if we start with real valued functions. So in other words, we consider the map phi goes to its extension phi evaluated at the point z. So this is a map that takes continuous functions on the boundary and gives us a real number. So in other words, it's a linear functional. This map defines a linear functional omega from, depending on z, from the continuous functions on the boundary to the real numbers. And some of the properties it has are, by the maximum principle, the absolute value of omega z of phi is less than or equal to the sup norm of phi. And if phi is positive, then its extension is positive, so omega z of phi is positive. And it's linear because the operator p is linear. If the solution, since the sum of two harmonic functions is harmonic, the solution for a sum of two boundary data is just the sum of the solutions for each one individually. So in other words, omega is evaluation at an interior point defines a positive linear functional on the space of continuous functions. In other words, it defines an element of the dual Banach space. Now, what is the dual to the space of continuous functions?
It's like the set of complex measures.
Yeah, that's right. And these are real valued functions. So it's the set of real measures. And in fact, it's the set of positive measure. The omega of z is a positive measure because it assumes positive values on functions. So what that means is that we have the following. I almost hesitate to call it a theorem because it's just an application of the Ris Representation Theorem, which says any such linear functional can be interpreted as a measure. So for all z in omega, we have a conformally natural measure omega z on the boundary of omega, characterized by the property that p of capital Phi evaluated at the point z is equal to the integral over the boundary of omega of phi, say of t, with respect to this measure omega z of t. And this measure is called the harmonic measure on boundary of omega, and often as seen from the point z. because the measure will depend on which point we're at. And one of the great things about measures is that although initially you are only integrating against continuous functions, you can actually integrate against any measurable function here, say a Borel measurable function. And so it defines a measure not just by integrating functions, but it defines a measure on sets. So given say a Borel set, A, contained in the boundary of omega, we write, this is just sort of standard notation, the harmonic measure on the boundary of omega as seen from Z of A as omega Z omega A. So in other words, this is the Z measure of the set A. And this object, which is called the harmonic measure of A, carries all the information about solving the Dirichlet problem on your region. If you know this measure, then you can solve the Dirichlet problem. It tells you, so to speak, what the Poisson kernel is for your region. So it's very closely related to the Poisson kernel when we know it. What makes this notion so powerful is that when we don't know it exactly, there are very simple procedures for estimating it. And this is a real theme in conformal invariant theory, is first we define something that uses only the conformal geometry of our region, and then we find ways to estimate it in concrete situations when we can't calculate it exactly. So this is the definition of harmonic measure. So let's look at some examples. So first, I'll let my domain omega be the unit disk, and I'll let Z be 0. So what's the harmonic measure on S1 when Z is equal to 0? Well, this is the measure. The answer is omega Z is d theta over 2 pi. Because the value of a function at the center of the disk is equal to 1 over 2 pi times the integral of phi of theta d theta. That's just the mean value property. Okay, so the measure induced on the circle by the choice of the point Z is the usual angular measure. What is the measure induced from a different point? So if Z is equal to R greater than 0, by the same token, the measure omega of Z is d theta, but now it's multiplied by the Poisson kernel, p of r theta times 1 over 2 pi. So the Poisson kernel is telling us how the harmonic measure on the boundary changes as Z gets closer to the boundary, say as Z moves along the positive real axis towards the point 1. When we're at the origin, we have democracy. That is, all the points on the circle are favored equally. But when R becomes more positive, we start to favor the states on the East Coast. The Poisson kernel, as R increases, blows up a little bit near 1, and it gets smaller than it used to be on the rest of the circle. And as R gets very close to 1, we get a function that's very peaked, has almost all of its mass there, and essentially vanishes on the rest of the circle. So the harmonic measure is telling you the relative importance of the different points on the boundary in forming the harmonic extension of our boundary data, capital Phi. Another way to say it is in the simply connected case, it's telling you the probability that a randomly chosen geodesic terminates in a given set, if it starts at the point Z. Okay, now, hopefully we can move beyond the unit disk, and we can. So another nice example is the upper half plane. So in H, this is really beautiful, the omega z H of AB, well, let me do one example with arcs here. So here, let me just say 1 prime, the harmonic measure in the disk from the origin of an arc on the unit circle is just the length of the arc divided by 2 pi. That's its harmonic measure as seen from 0. Here it's the integral of the Poisson kernel over that arc. In the upper half plane, we can pick a point AB, an interval AB, and we can pick a point Z in the upper half plane, and we can say, what is the harmonic measure of this set A? And there's a beautiful formula for it, namely the harmonic measure of this interval as seen from Z is equal to alpha divided by pi. And in fact, whenever we fix a set A here and let Z vary, this function omega Z omega little omega of Z omega A is a harmonic function of A itself, of Z itself. So let me remark that omega Z capital omega A is just equal to the harmonic function with boundary values, the indicator function of A. So I claim that the harmonic measure of this set A, an interval from A to B in the upper half plane, is just the visual angle using Euclidean geometry of the set A divided by pi. In this case, even when you get very close to the boundary, the interval doesn't occupy your full visual sphere, but it occupies almost 50% of it. So this angle gets closer and closer to 180 degrees, and the harmonic measure tends to 1. When you get very far away, the harmonic measure tends to 0, but you also might try to keep the harmonic measure constant, and the level sets of harmonic measure turn out to be just circular arcs that are centered that rest on these points. So in fact, you can come down towards B, and if you approach it along this circle, the visual angle of A will remain a constant. Okay, so how do we know this? Well, again, this is because we know exactly what this harmonic function is. That should be 1 here and 0 here. It is exactly the argument of Z minus B minus the argument of Z minus A divided by pi. And the difference in these two angles is this angle alpha here. So this is kind of interesting. In the unit disk, if we wanted to compute by the same token, if we were at a point Z which is not at the origin, and we wanted to compute the harmonic measure of an arc A, we could go plug into the Poisson kernel, but there's also a geometric description of this, which we've studied. Namely, you form the hyperbolic geodesic here, and you form the hyperbolic geodesic here, these two hyperbolic geodesic rays that go to the endpoints of A, and then this angle, beta, it tells us the harmonic measure of A. So in the disk, omega Z delta A is this angle beta divided by 2 pi. And this angle is defined using hyperbolic geometry. This angle is defined using Euclidean geometry. So it follows, so you'll notice that these lines are not hyperbolic geodesics because they don't meet the boundary at 90 degrees. It follows that if we were to form the hyperbolic geodesics from Z to A and B. So if we were to try to form the hyperbolic geodesic, which would go something like this, and then the hyperbolic geodesic here, which would go something like this, then we get a different angle beta here, and that beta would be exactly equal to 2 alpha. So that's a little exercise in plane geometry. Okay, so that's the harmonic measure of some specific sets in the upper half plane. What is the harmonic measure itself? So the basic harmonic measure on the disk is the harmonic measure as seen from 0. In the upper half plane, all the points are pretty equivalent, so we might as well take our base point to be I, and the harmonic measure on the boundary of the upper half plane, given by omega I, is nothing more than dx over 1 plus x squared with a 1 over pi thrown in to make this have integral equal to 1. Okay, so this harmonic measure peaks near 0, and then it flows off to infinity. And you can think of this as, again, the distribution along the real axis of the endpoint of a hyperbolic geodesic ray that leaves I at a random angle. But you could also think of it, by virtue of what we've discussed just a moment ago, in the following way: you choose an angle between 0 and pi, and then you draw a line with that angle alpha and see where it hits the real axis. And you get this so-called Cauchy distribution on the real axis, which is given by this density. Now, this density should be familiar to you from complex analysis. What do you get if you integrate this function?
Arctan.
Yeah, right. This is our old friend arctan. So the integral of this density is the arctangent of x. And that fits with what we've discussed before, because if at this point I, you have a right triangle going out to the point x, and so this length here is x, this length here is 1, and the tangent of the angle alpha is equal to x over 1, which is just x. So the arctangent of x is giving you this angle alpha. And so if you take the difference between these arctangents at 2 different points A and B, you get the definition. You get this, I've erased it now. You get the harmonic measure of an arc on the boundary of a hyperbolic plane as seen from the point I. Okay. So one last example, and then next time we'll see how you use harmonic measure to estimate and control analytic functions, and also how you get kind of a feel for how harmonic measure works. Our final example is we're going to do for once a multiply connected domain. So we have our friend A of R, which is the annulus of outer radius R and inner radius 1. And rather than doing the harmonic measure in general, I'm just going to take the set A to be the outer boundary. So it's the circle of radius R. So I'm going to be interested in a function which is 1 here and a function which is 0 here on the inner boundary, where the absolute value of z is 1. And I want to construct the harmonic measure. So I want to know how much influence does the outer boundary have on the value of harmonic function at z versus the inner boundary. And so that quantity is the harmonic measure in z through this annulus AR of the outer boundary, which is the circle of radius R. And this is luckily yet another example that we can write down explicitly. And you can kind of guess what it should be, because if this were a tin can, if we change coordinates so it was vertical like this, then it's pretty clear the harmonic function would just be the height function on this tin can. And this tin can is related to the annulus by the exponential function. So in fact, omega of ZAR is just the logarithm of the absolute value of Z. So this certainly is equal to 0 on the inner boundary, and it's harmonic in our domain, and it's constant on the outer boundary. The only problem is the constant is R. So we put a log R in here. And that tells us the harmonic measure of the outer boundary if seen from an arbitrary point, Z, in between the circles of radius 0 and 1. Okay, so we'll show that this simple calculation plus a general argument leads to many estimates in complex analysis, including something called Hadamard's three-circle theorem. Okay, so next time we'll move back towards complex analysis and finish harmonic measure, and then we'll move on to capacity and extremal length, and that should be enough foundations to begin the probabilistic discussion of potential theory in the complex plane. Okay.
Professor,